You know, we often think of solid materials as just that solid, but have you ever stopped to consider the unseen forces, the stresses at play within them?
Hmm.
Think about something like, say, an aircraft wing. Those composite plates look strong, uniform,
Right.
but after even a small incident, maybe something bumps into it, hidden stresses can actually get locked inside.
Exactly. And it's remarkable how these everyday interactions, whether it's just like slow pressure or a more sudden knock, maybe a dropped tool,
Yeah,
how that can create these lingering internal stresses, stuff you just can't see.
absolutely. And that's exactly what brings us to today's deep dive. One of you shared a really interesting research paper with us.
Oh, great.
Yeah, it's titled Influence of Contact Interaction Character on Residual Stresses Arising Over Damaged Area in Composite Plate. It's by Pisarev and colleagues,
Okay.
published just this year, 2025, in Fracture and Structural Integrity. And the researchers, they're from some top places, TSAGI, the Central Aero Hydrodynamics Institute,
Ah, yes. TISA's AGI.
the Mechanical Engineering Research Institute of the Russian Academy of Science, and also UAK Yakovlev.
Okay, so some serious aerospace and engineering background there. This paper sounds like it gets into a really critical area then.
It really does.
Understanding these residual stresses, the forces left inside these advanced composite plates after they get damaged, whether it's a slow contact or a sharp impact.
So our mission for this deep dive is pretty clear. We want to pull out the key insights from this paper, really get a handle on how different kinds of contact, different impacts affect these internal stresses,
Mm.
and maybe more importantly, figure out why knowing this stuff is actually so crucial in the real world.
Well, one of the biggest challenges with composites is really assessing the damage properly. The usual methods, the traditional non-destructive testing.
Like ultrasound or CT scans.
Exactly. Ultrasound, computed tomography, even infrared thermography. They're useful, sure, but they often give us sort of indirect information. You might see hints, like tiny cracks in the resin matrix, or maybe layers starting to separate, that's delamination, or even broken carbon fibers.
Right, clues, but not always the full picture, quantitatively speaking.
Precisely. These established methods, they often struggle to give us those really reliable numbers, the design criteria we need to predict how well a composite will hold up after an impact, especially across different types of composites.
But this is where it gets really interesting, right? This research is suggesting that maybe looking at the residual stresses themselves, right, in the damaged area,
Yes.
that could be a much more direct, more reliable way
Yeah,
to gauge the risk.
that's a really fundamental point they're making. If you understand these leftover stresses, you get a direct link between the physical damage you observe and the actual internal forces.
Okay.
And that's incredibly valuable. It helps improve our computer simulations, our numerical models,
Hmm.
and ultimately helps us predict the strength and the durability, the lifespan of these structures much better.
So how did they actually do it? How did these researchers go about, investigating these hidden stresses? What were the experiments like?
Okay, so they focused on a specific material, carbon fiber reinforced polymer, CFRP.
Right.
The specific type they used had a particular layer stacking sequence. They note it as 6090S. You can think of it like layers of fabric where the carbon fibers are oriented at specific angles.
To give strength in different directions.
Exactly. Gives it tailored properties. The samples were 180 by 30 millimeters. And interestingly, they used a slightly thicker plate, this time 6.4 millimeters, compared to 4.8 in some prior work they reference.
And they really nailed down the material properties too, didn't they? The sort of fundamental ways it responds to force, the elastic properties.
Oh yeah, very meticulous. They list the longitudinal and transverse moduli, how stiff it is along and across the fibers, both 73.1 GPa.
Okay.
The shear modulus, how it resists twisting, 5.3 GPa. And Poisson's ratio, how much it thins when stretched, 0.25.
And they figured that out using vibrations
Mm.
by hitting it and seeing how it rings.
Basically, yeah. Analyzing the impact-induced vibration modes, and that's a clever way to get those bulk properties.
Okay, so meticulous setup. Then the actual tests. They looked at two main scenarios, slow versus fast contact.
Right. Two types of contact interaction. First, static indentation. That's the slow press. They used a smooth 16 millimeter diameter steel ball and just pushed it into the composite.
Gently or with some force.
With a controlled force of 3.0 kilonewtons, they labeled those samples CPS for static.
Okay. And the second type, The dynamic impacts.
That's where they use a drop weight tester, basically dropping a weight with a specific impactor shape onto the sample.
Right.
They used two different hemispherical impactors. One was 20 millimeters in diameter, that coupon was CPD-20.
Right.
The other was a bit larger, 25 millimeters CPD-25.
And the energy was the same for both impacts.
Yes, both delivered 55 joules of impact energy. And they do mention, it's useful context, that a previous study used that 20 millimeter impactor, but at a lower energy, 40 joules, on the thinner 4.8 millimeter plate.
So they're building on previous work, comparing different impactor sizes and energies, and also thickness.
Got it. Mm.
But how did they actually measure the stresses afterwards? You can't just put a strain gauge inside, can you?
No, it's much more subtle. This is where their method gets really clever. They drilled tiny holes, just 2 millimeters in diameter, very close to the damaged areas.
Tiny holes. Okay.
And then they use a technique called electronic speckle pattern interferometry, ESPI.
ESPI. Sounds complex. What does it do?
Think of it as a highly sensitive optical method. It uses lasers to measure how the surface of the material moves, like incredibly small movements, when that tiny hole is drilled.
So drilling the hole relieves some of the locked-in stress right around it.
Precisely.
And the ESPI measures how the surface relaxes or shifts as that stress is released.
Exactly. It measures the local deformation field.
Hmm.
And doing that tells you about the stored up energy, the residual stresses that were holding it in place.
Wow. Was it tricky to get good measurements, especially on, say, a painted surface?
It definitely can be. Painted surfaces can sometimes mess with these optical techniques, but the paper states they were successful. They managed to get high-quality interference fringe patterns.
Fringe patterns,
Yes.
like contour maps of the deformation.
Sort of, yeah. These patterns, these fringes, visually represent the displacement field caused by drilling the hole.
Okay.
And by analyzing the shape, the density of these fringes, they can calculate the principal residual stress components. They call them sigma 1 and sigma 2.
Sigma 1 and sigma 2.
Yeah.
Those represent the stress acting along the material's main directions, right? Like along the fibers and perpendicular to them.
Essentially, yes. Along the material's principal axes of anisotropy, it tells you the magnitude of the stress in those key directions.
Okay, so a really sophisticated way to measure these hidden stresses.
Mm-hmm.
So they did all this. Stress the plates, measured the outcome. What were the big takeaways? What did they find comparing static versus dynamic?
Well, first off, doing the static indentation test was partly to confirm the ESPI method itself worked reliably on their painted composites.
A validation step. Smart.
Exactly. Once they were confident with that, they moved to the impact damage. One thing they noted across the board was that the stress distribution wasn't perfectly symmetrical around the impact point.
Why not?
They figured it was due to some pre-existing stresses already in the material, probably from the manufacturing process itself.
Oh, right. You mentioned that earlier. Technological residual stresses.
Yep. They even measured the average background levels, about plus 13.9 MPa for sigma 1, and a higher plus 48.6 MPa for sigma 2. Positive values mean tensile stress, pulling.
So the material isn't perfectly neutral to begin with. Interesting. What about right at the edge of the dent, the dimple?
Okay, at the contour of that indentation or dimple, they found the tangential components, the stress acting around the curve, were tensile, pulling outwards.
For both static and dynamic.
Yes, in both cases.
Yeah.
The radial components, acting like spokes towards the center, were generally compressive, pushing inwards. Although it got a bit more complicated with the larger 25 millimeter impactor, the CPD-25 sample.
Okay. And did changing the impact parameters, like the impactor size at the same energy, make a big difference? Comparing the 20 millimeter and 25 millimeter impacts at 55 joules.
It did. That comparison was quite revealing. They found that with the smaller 20 millimeter impactor at 55 joules, remember that was higher energy than the previous study.
Right, 40 joules before.
It actually caused more visible surface damage, cracks and stuff, which unfortunately made it harder to get reliable stress measurements right in the center of the impact zone.
Okay, so more energy, smaller point,
Yeah.
more concentrated damage, harder to measure the stress accurately instead.
Pretty much. But when they used the larger 25 millimeter impactor, delivering that same 55 joules,
Spread the force out a bit more.
exactly, they got more reliable data, both inside the dimple and just outside it. It suggests that with that larger impactor, they could probably even increase the impact energy further and still get good stress measurements.
Interesting. And what about the magnitude of these stresses? Were they, significant enough to be worrying in terms of the material strength?
Oh, absolutely. This is crucial. For that 25 millimeter impact case, the CPD 25 coupon, they measured a peak tensile residual stress component, sigma 2, of plus 123.8 MPa.
Okay. 123.8 MK. How does that compare to the material's breaking point?
Well, they state the ultimate tensile strength for the CFRP is somewhere between 750 and 800 MPa.
Wow. So 123.8 compared to, say, 800,
It's
that's
about 15.5% of the ultimate strength.
15%. Just from a single impact, that's a significant chunk of its strength already used up, just sitting there as residual stress.
It really is. That's a substantial pre-stress that could seriously increase the risk of fatigue failure down the line, under repeated operational loads.
That really brings home why this matters, a hidden weakness.
Definitely. They also saw something interesting within the dimple itself. That sigma 2 component actually transitioned from being compressive, pushing in, to tensile, pulling out as you moved across the indentation.
A stress gradient, a sharp change.
Exactly. And sharp stress gradients like that are generally bad news for material strength.
Okay. Any other key stress findings? You mentioned compressive stresses too.
Yes, highly significant compressive stresses right at the center of the dimple. For the static case, sigma 2 was negative 230.9 MPa. Negative means compression.
Minus 230, that's huge.
It is, and even for the dynamic 25 millimeter impact, it was medical 173.0 MPa. That level of compressive stress could mean the material loses some of its bearing capacity in that spot, its ability to resist being crushed or squeezed.
So impacts can cause both dangerous tensile and compressive residual stresses.
Correct. And interestingly, they noted, referencing one of their figures, that the overall pattern of this sigma 2 stress along the vertical center line was actually quite similar between the static press and the dynamic impact.
So different causes, but a somewhat similar stress signature in that specific location.
Yeah.
Fascinating. Now, what about the thickness? You said they used the thicker plates this time. How did that change things compared to the earlier, thinner samples?
Right, comparing their 6.4 millimeter thick plates to the 4.8 millimeter ones from the prior study for the slow static indentation. Making the plate thicker led to a pretty noticeable decrease in those compressive residual stresses along the vertical axis. Sigma 1 dropped by 14%, and Sigma 2 dropped by a really significant 51%.
51% lower compressive stress just by adding, what, 1.6 millimeters of thickness?
Seems so for that specific loading case and measurement axis. The horizontal components didn't change much, though.
Okay, so thickness helps reduce those central compressive stresses in the static case. What about for the dynamic impacts, comparing thick and thin?
They looked at the 20 millimeter impactor data. Now remember, for the thicker plate, they used more energy, 55 joules versus 40 for the thinner one.
Right.
But even with that increased energy, the residual stress components measured along the horizontal axis actually decreased when the material was thicker.
Interesting. So even with a harder hit, the thicker plate showed lower stresses horizontally. It seems thickness generally helps mitigate these residual stresses, at least in some ways.
It appears that way from these results, yes. It adds complexity, but it suggests thickness is a really important parameter here.
Definitely. Now, the study went one step further, right? They didn't just look at the stresses right after impact. They looked at fatigue. What happens over time with repeated loading?
Exactly. This was a really interesting part. They took one of the statically indented samples, CPS, and then put it through fatigue testing.
Okay.
Subjected it to 1.1 million cycles of push-pull loading. A specific stress range, equals 318 MPa, with a stress ratio R equals 0.5. Think of it like simulating the wear and tear an aircraft part might see over many, many flights.
1.1 million cycles.
Okay.
And then
Then they went back and measured the residual stresses again, right at the center of that original indentation, and compared the before and after values.
And what happened after all that cycling? Did the stresses change?
Dramatically, they found a huge relaxation. It's a big decrease in that sigma 2 component, the one acting along the direction they applied to fatigue loading.
How big a decrease?
It dropped by 79.2%, almost 80%.
Wow. Nearly 80% of that central residual stress just dissipated after the fatigue cycling.
That's what they measured. And this is a really powerful finding. It strongly suggests that you could potentially use residual stress measurement as a way to track fatigue damage accumulation.
Like the stress level tells you how much fatigue life might be left?
Potentially, yes.
Yeah.
It opens up the possibility of using it as a quantitative indicator. As the stress relaxes, it signifies damage processes are occurring.
That has huge implications for maintenance and safety checks. So these stresses aren't necessarily permanent fixtures.
No, they evolve under load, which is why monitoring them could be so valuable for predicting the remaining life of composite structures.
Okay, let's try and wrap this up. Putting it all together, what's the big picture from this research? The overall significance.
I think the main takeaway is that these residual stresses, these hidden internal forces near impact damage, are not trivial. They significantly reduce the strength of these CFRP materials, whether you're pulling on them or compressing them.
Reduces the safety margin.
Exactly. And secondly, the fact that these stresses change, specifically they relax, under cyclic loading, that points towards a potential new way to quantify fatigue damage progression.
It really underscores that we need to look beyond just the visible damage, right?
Yeah.
These internal forces are critical for understanding how long structures will last, how reliable they'll be.
Absolutely. And the researchers are clear. The interplay between thickness, impact energy, impactor size, and the resulting stress field is complex. More work is needed with a wider range of parameters.
Sure.
But this study provides a really solid foundation. It shows the potential of using residual stress measurement as a critical tool, both for understanding damage mechanisms and for predicting failure, especially in safety-critical applications like aerospace.
So just to recap this deep dive for everyone listening, we've journeyed into the world of composite materials and found that impacts, even seemingly minor ones, leave behind these complex patterns of hidden stress.
Residual stresses.
These stresses can seriously compromise the material's strength from the get-go. And crucially, how these stresses change over time under repeated loading gives us vital clues about fatigue and potential failure. It's a reminder to look deeper than the surface.
Well said. And thinking about that huge, nearly 80% reduction in residual stress after the fatigue cycles, it really poses an interesting question for you, the listener, to mull over.
Okay.
With this knowledge, knowing that stresses can relax but also cause initial weakness, how might engineers actually approach designing composite structures differently? Could they design them, or perhaps even design the material itself, to better manage or mitigate the long-term effects of these inevitable impacts and the fatigue that follows?
Designing for stress relaxation or maybe pre-stressing components beneficially. Definitely some fascinating food for thought there. If you want to dig deeper into this, we absolutely recommend checking out the paper itself and the prior work it cites. It's a rich area, this intersection of non-destructive testing and material science. Until our next deep dive, keep thinking, keep questioning.